Okay, welcome back. We're still talking about discrete time convolution. So I've got an example here. Determine the response of an LTI system whose impulse response h of n and input x of n are these two functions. So I've got them mathematically written here. X of n is 1 when n is between 0 and 4, 0 else. H of n is this alpha to the n when n is between 0 and 6, 0 else. And alpha is a constant. Okay, so let's first, before we get lost in the mathematical details, let's take a moment to talk about engineering, which is what this course is about, of course. So we've got an LTI system, and the goal is that I want to put in this signal x of n specified in the problem, and I want to figure out what I get out of the system. And I know that the system is linear, time invariant. Okay. Well, and I'm not going to perform circuit analysis or mechanical analysis or whatever. Instead, all you have to do is tell me how it responds to an impulse. Tell me how the system responds to an impulse. That's h of n. That's also given in the problem. And then I don't have to perform circuit analysis or mechanical analysis or whatever. All I do is convolve the input, whose output I'm trying to find, with the impulse response. And that tells me the output. I'm going to need some space, so I'm going to erase that. All right. Now, this is not hard. I want to put this in context before we get started. This is not hard. Okay, let's put this in context. Going to war is hard. Losing a loved one is hard. This just requires focus. This is graphing. This is multiplying and adding. None of that is hard. But it requires your focus, and this problem particularly requires focus. So if your roommate is being annoying, if your kids are crying, do what you have to do, remove yourself from those distractions, and focus. Now, I've plotted, I guess before the plot, notice the convolution sum is in terms of k, really. We've got x of k, and then if we take the perspective of k, we've got h of n minus k. So I've plotted both of these signals versus k. So here's x of k, right? Between 0 and 4, I've got 1, and then 0 else. And then because minus k appears in h, I've plotted h of minus k. So I've replaced n's with k's, and then I've flipped it. Okay, so now this thing is non-zero between 0 and minus 6. And my plot is kind of squeezed in there. So it's important to note that at minus 7, this thing becomes 0 and stays 0 for minus 8, minus 9 to minus infinity. All right, so first notice that the n in this formula then, with the perspective of k as being the independent variable, the n is shifting h around. So if I shift h, or the reflection of h, by n that is at least to the left by 1. So if n is shifting by less than or equal to -1, meaning we're shifting to the left at least 1 unit, then, so imagine this plot shifted to the left by at least 1, then there's no non-zero overlap between these two plots. So no non-zero overlap means that this product between x and h would be 0, and then I add up a bunch of zeros, and so y is also going to be 0. So right away we've got a piece of the output. This is going to end up being a piecewise function. So we see that a piece of the output is this. When n is less than or equal to -1, the output is going to be 0. So we're going to remember that. Now, let's say I shift by n equals 0, meaning I don't shift at all. The non-zero overlap is between k equals 0 and k equals 0, meaning there's just really this one point of non-zero overlap. Okay? And if I shift by n equals 1, so imagine this plot, h of minus k, shifted to the right by 1 unit, you're going to have to use your imagination because I'm not going to draw this every time. The non-zero overlap would now be between 0, because this graph is static, and 1, k equals 1. So we're looking for a pattern between the regions of non-zero overlap and what n is. So if I shift h of minus k by 2, you can imagine the non-zero overlap would be between k equals 0 and k equals 2. If I shift it by 3, the non-zero overlap is k equals 0, k equals 3. So do you see a pattern here? You should. Now, if I shift by 4, so imagine this plot. It's easy to go through this quickly, but let's slow down for a second. Imagine this plot shifted to the right by 4 units. That would bring this leading edge to 4, and this leading edge, or this back edge, to minus 2. So the non-zero overlap is still between k equals 0 and k equals 4. Now, notice that when I shift by n equals 5, so this leading edge at 0 would now be at 5, which is outside of this range, right? Because this one stops at 4. And then this leading edge would be at minus 1. So the non-zero overlap now is k0 to k equals 4. Pause the video. If you want, take a second to digest that, but I'm moving on. So you'll notice there's a paradigm shift here. We thought we had a pattern, and now the pattern seems to change. And so we're going to attack this pattern first. And then, so this is the region when n is at least 0, but less than or equal to 4, right? And the pattern seems to be k goes from 0 to k goes to n. Okay, so I'm going to erase this. Now I'm going to work on my convolution sum. So again, for this range of n, y of n is, now I don't need to add up infinity number of zeros, right? Because outside of this range, those terms are 0. The range of non-zero overlap was k goes to 0 to k goes to n. Now in that range of non-zero overlap, my signal x is 1 because it's non-zero. So I'm not even going to write the 1 there. H of n minus k, well here's h of n, right? We want the non-zero part. So that's h of n. H of n minus k is alpha to the n minus k then. Now, we have to evaluate this summation. So this can be written, I can use a property of exponents as alpha to the n, alpha to the minus k. And because alpha to the n does not depend on k, the indexer, I can bring it out. And then alpha to the minus k is the same thing as 1 over alpha to the k. All right, and I want to recall, I'm going to write it off to the side in red, in green, the partial sum formula from mathematics. It's called partial because this thing here is not infinity. It's finite, so it's a partial sum. And it says that the sum of k equals 0 to n of alpha to the k is 1 minus alpha to the n plus 1 over 1 minus alpha. Okay, so this is just something that we take from mathematics. So we look at what we have. Well, we have 1 over alpha. So 1 over alpha is our constant. So this thing, and we have this alpha to the n hanging around. So now 1 over alpha. So I replace alpha with 1 over alpha. This is 1 over alpha to the n plus 1 over 1 minus 1 over alpha. Okay? And so if I like, I can distribute, just to simplify this a little bit, distribute the alpha to the n in. So this is alpha to the n minus, and I have alpha to the n divided by alpha to the n plus 1. So that's alpha to the minus 1, right? Same bases, subtract the exponents over 1 minus 1 over alpha. And if I multiply everything by alpha, I get alpha to the n plus 1 minus 1 over alpha minus 1. And usually this is written, if I pull out a negative from both the numerator and the denominator. And look at that. We actually have the same thing. That's very nice. Okay, so this is part of our solution. And I say part, it's just a piece. This is going to be piecewise. This only applied for when n was between 0 and 4. Now, let's continue shifting by 5. And that we said that the non-zero overlap was between 0 and k equals 4. Now let's shift by 6. So if we shift by 6, that brings the minus 6 edge all the way up to 0. Okay, that aligns with this non-zero. And then that brings the 0 to 6. This leading edge is now at 6. So we're still going from 0 to 4 because the 6 falls outside of this window. So the non-zero overlap is between 0 and k equals 4. Okay, so it looks like now our window, or of our region of non-zero overlap, is just constant. It does not depend on k. So that's kind of the pattern, if you want. And notice that if I shift by 7, that brings this minus 6 all the way to 1. And that brings this 0 now to the origin. So I'll draw it in red, I guess. So if I shift this thing by 7, I would have a 0 here, right? Because that's the minus 7 gets shifted up here. So these are all zeros. And then this non-zero at minus 6 is at 1. I've got something like this. And so on, right? This 0 gets shifted. Okay, but the important part here is now, at n equals 7, the range of non-zero overlap does not start at 0 anymore, because this leading edge has been shifted up to this point. So it starts at 1 and goes to 4. So we seem to have a paradigm shift here, a change in the pattern. So once we see a change in the pattern, we just need to consider this. Okay, so this is for 5 and 6. And the range of non-zero overlap is k equals 0 to 4. Right. I'm writing that down again because I'm going to erase this. And so again, I'll write it here, 5 to 6. My convolution sum becomes a sum, k goes from 0 to 4. X is 1 in the non-zero part. H, I've got it outlined in orange here, is alpha to the n minus k. Okay, that's h of n minus k. So now I have to solve this summation. Okay, well, this looks a lot like the summation that I just did, except n is 4, right? So I can just plug in n equals 4 to my result. This gives me 1 minus alpha to the 5 over 1 minus alpha. Okay, so for this region, I have this. Okay, now I'm going to erase the partial sum formula. No, I'm going to need the partial sum. All right, I'm going to squeeze this into the bottom here. So let's say now I shift by n equals 7. We said that k goes from 1 to 4. And if I shift by n equals 8, that would bring this minus 6 up to 2. Okay, so then I would be adding from 2 to 4. And when n is 9, that would bring the minus 6, that back edge, all the way up to 3. So this would be k equals 3 to 4. And when n is 10, I would be going from k equals 4 to 4. Now when when n is 11, now I overshoot the whole thing. Minus 6, when I shift by 11, becomes 5, which is outside of this range, and anything more than that, there's no non-zero overlap. So we can just kind of say up here when y was 0, this also applies for when n is greater than or equal to 11. When n is greater than or equal to 11, we overshoot and there's no overlap. Okay, but let me take care of this now. So for n, excuse me, 7 to 10, my convolution sum becomes a sum from k equals, okay, now what is the lower bound? It seems to be changing with n. Can you find a pattern? When n was 7, the lower bound was 1, 8, 2, 9, 3, 10, 4. So in general, it looks like it's n minus 6. And the minus 6 comes from the fact that this edge is at minus 6. And then in all these cases, we sum to 4. N minus 6 to 4. And again, in this range, x is 1, the non-zero overlap, and h of n minus k is alpha to the n minus k. All right. So I'm going to have to solve this summation. Okay, so the way I can do this, and notice it does not match the partial sum formula. I don't have a k equals 0 here. All right, but what I can do is this is called a change in variables. I'm going to let, how about k hat, so just some variable, some different variable, k hat equal, how about, what do I need to make it a 0 here? K minus n minus 6. So when k is n minus 6, k hat is 0. You see, take a second to make sure you get that. So we're gonna exchange the k's with k hats. We're changing the index. When k is n minus 6, k hat will be 0. Okay, so I'm going to write this as a sum from k hat equals 0. This is change in variables. And then when k is 4, k hat is 4 minus n plus 6. So that looks like 10 minus n to me when k is 4. Okay, so I've got my bounds for this new variable k hat. I've changed the index. Now I've got n, or alpha to the n. I had minus k before, so if I solve this little let statement for k, or minus k, I guess, okay, notice that k is k hat plus n minus 6. Then I have alpha to the n minus k hat plus n minus 6. Okay, again, pause the video if you want and make sure this is all making sense. Focus. Okay, I did a change in variables wherever there was a k, I got rid of the k's and I made k hats. Now, I've got k hat running from 0 to 10 minus n. I've got alpha to the n. I've got alpha to the minus k hat. I've got alpha to the minus n. And I've got alpha to the 6. Okay, I'm running out of space. I'm going to come over here by the asterisk. Alpha to the n and alpha to the minus n, when you multiply them, they cancel. Same base, add the exponents. Alpha to the 6 is a constant. It can come out. So I've got alpha to the 6, k hat, 0 to 10 minus n, and then alpha, and then I'm going to change this to 1 over alpha, right? I can do that to the k hat. Now I can use the partial sum formula. See, now it's in the form. I've got an indexer starting at 0 and going to some bound. Then I've got some constant to that indexer. So I can use the partial sum formula. So I've got alpha to the 6 times 1 minus 1 over alpha, that's my constant, to the partial sum formula says the top bound plus 1. So the top bound is 10 minus n, plus 1 is 11 minus n, over, partial sum formula says 1 minus the constant, 1 minus 1 over alpha. Okay, so now I've solved the sum. I can bring the alpha to the 6 in if I like. So this is alpha to the 6 minus. So this is alpha to the 6 over alpha to the 11 minus n. So subtract the exponents. This is n minus 5. Alpha to the n minus 5, it looks like. And I've got 1 over 1 minus alpha here. Okay, I'm going to erase this. Now, just to clean this up a little bit, multiply the top and the bottom by alpha. So this is alpha to the 7th minus alpha to the n minus 4. Right? Add the exponents over alpha minus 1, and usually this is written by taking a negative out of both the numerator and the denominator. Alpha to the n minus 4 minus alpha to the 7th over 1 minus alpha. Okay, and so that is the answer to our sum, right? And that applies for this piece here. So we've got the entire, I'm going to erase the partial sum formula. We've got the entire solution now. And I'm actually going to erase the work. Right, I'll erase the plots to give me some space. Okay, the solution. The convolution of x with h is a piecewise, and it has 1, 2, 3, 4 pieces. Okay, we'll save the y equals 0 part for the last. So when n is between 0 and 4, this piece occurs, or applies, I should say. 1 minus alpha to the n plus 1 over 1 minus alpha. So this is between 0 and 4. Next, piece 3, this applies here. 1 minus alpha to the 5th over 1 minus alpha. That's actually a constant. That's interesting. This is between 5 and 6. Okay, piece 4, alpha to the n minus 4 minus alpha to the 7th over 1 minus alpha. This is between 7 and 10. And then the last piece, so I think I need my curly brace to be extended, is 0, right? This is piece 1. 0 when n was less than or equal to minus 1, or when n is too large. So we'll just say we'll say else. That's it. That's the answer. So you see how, you need to work with these things a little bit to be able to figure out the pieces, how to set up the sum, how to evaluate the sum, and so on. So if you wanted to plot this, you could pick a value for the constant alpha, and then you can plot it and take a look at what it looks like.